All right, today we are diving into one of the most elegant and, honestly, influential ideas in all of computer science, communicating sequential processes, or CSP for short. It's basically a formal language that helped us tame the absolute chaos of concurrent computing, and you can still feel its impact today. So let's get right into it.
Just stop and think about that for a second. Your phone, the internet, the entire global financial system. All of them are juggling countless things at the exact same time. So how does all of that not just fall apart? How do we keep it from melting down into total chaos? This is the exact problem that CSP was designed to solve.
The challenge really is all about orchestrating complexity. It's like trying to conduct a massive orchestra filled with millions of digital tasks. The goal is to make sure they all play in perfect harmony, instead of just creating a mess of errors and noise.
So let's really try and grasp the sheer scale of this challenge we're talking about.
Every single time you tap your screen, click a mouse, or make a purchase, there are multiple processes firing off, all running at the same time, all needing to communicate and coordinate perfectly. Without a really solid framework to manage this, nothing, and I mean nothing we rely on would be possible. This isn't just some abstract puzzle for academics, it's the very bedrock of our digital lives.
So how on earth do you tame that kind of complexity? Well, the answer lies in an idea that is so simple, it's beautiful, but it's also incredibly powerful.
The key to this whole thing is right here, compositionality. This is the hero of our story. The idea is, instead of trying to understand a massive, complicated system all at once, which is basically impossible, you focus on the small, simple, predictable building blocks and the clear rules that tell you how they connect.
Think of it like playing with Lego bricks. It's the perfect analogy. Each individual brick is simple. It's predictable. You know exactly what it does. But by combining them according to a really clear set of rules, you can build these incredibly complex, stable structures. CSP applies that exact same logic to software. You start with simple processes, you define exactly how they're allowed to talk to each other, and suddenly you can build these huge, robust systems that you can actually understand and trust.
And this brings us to the guy who literally wrote the instruction manual for this whole idea, the brilliant computer scientist C.A.R. Hoare. We have to go all the way back to 1978. Hoare publishes this now legendary paper that lays out the entire mathematical and logical foundation for CSP. And you got to understand, this wasn't just another programming language. It was a whole new way of thinking about how programs could work together.
And this quote right here, it kind of shows off the genius of it. CSP built on these already powerful ideas, like Dijkstra's guarded commands, which is just a fancy way for a program to say, I'm going to wait right here until a specific thing happens. Hoare took that and added two crucial ingredients, concurrency, so things could happen at the same time, and synchronous communication, which is like a very strict handshake for how they talk. That combination, it was a total game changer.
So the most important point is this. CSP models the world as just a collection of simple agents. It doesn't really care what the agents are doing on the inside. It is intensely focused on how they interact with each other. This focus on communication is what makes it a cornerstone of something called process algebra, which, sounds complicated, but you can just think of it as algebra for processes. It's using math to formally describe and prove things about how systems communicate.
But here's the really cool part. CSP wasn't just some abstract theory stuck in an academic journal. No way. It had a massive impact on the real world, inspiring actual hardware and software. The principles that Hoare laid out were so clear and so powerful that they became the direct inspiration for engineers who are out there building the next generation of technology.
And here are some of the big ones. A whole programming language, called Occam, was created to be a direct software version of CSP's ideas. That language was then used to program a revolutionary piece of hardware called the Inmos Transputer. And beyond that, the mathematical rigor of CSP allowed engineers to formally prove that safety-critical systems, things in airplanes or medical devices, were actually correct.
And we can't just gloss over the transputer. This thing was a huge deal. It was the first microprocessor that was designed from the ground up from day one for parallel computing. It was a perfect physical example of that Lego brick philosophy of simple communicating parts.
This slide really captures the paradigm shift that CSP caused. Before, trying to verify that a concurrent system worked correctly was, it was a nightmare. But with CSP, you could build systems from parts that you could prove were correct. You could even prove, mathematically, that a system would never get stuck in a deadlock, where two processes are just waiting on each other forever.
For building safe, reliable software, this was absolutely revolutionary. Now, the transputer itself might be a museum piece today, but the influence of CSP is stronger than ever. Its core ideas are still echoing all throughout computer science. The way we think about channels in the Go programming language, or the whole actor model in other languages, even modern microservices architecture, they all have CSP's DNA in them. It's all about isolated processes communicating over explicit channels. Hoare's big idea fundamentally changed the entire conversation.
And as you can see here, CSP is part of a whole family of these so-called process algebras. It's got a famous sibling, Robin Milner's Calculus of Communicating Systems, or CCS. Now, they differ on the technical details. For example, CCS focuses more on the interleaving of actions over time, but they both share that same foundational goal, bringing mathematical rigor to the very messy world of concurrent processes.
And that brings us right back where we started. That core principle we talked about. Composability is more vital today than it was back in 1978. In a world of distributed systems, cloud computing, and the Internet of Things, the only sane way to manage this exploding complexity is to build things from simple, understandable, and composable parts. CSP gave us a powerful blueprint for its time. But as our systems become exponentially more complex, it leaves us with one final question to chew on. What's the next great idea we're going to need to orchestrate the digital harmony of the future? Thanks for watching.